Hello, everyone. My name is Marcus Kjellander from the Noah's Ark lab at Huawei. And on behalf of my team, which consists of myself, my colleague Rao Zhongwen, also at Noah's Ark lab, and Chang Zhengzhi at State Street Corporation, I will present our approach to the KDD Cup spatial dynamic wind power forecasting competition held by Baidu. And in this competition, we participated using the team name Dida Dida Huala Huala, and we got rank 6 in the regular track. So before going into the details of the model itself, I want to say a couple of things regarding the data pre-processing and feature engineering. We found empirically that the feature engineering step played a critical role for obtaining a good final score. So this is an important part of our solution. And the figures here, they illustrate the feature importance for our task. So in other words, predicting the active power of the wind turbines. We have here separated it into 3 figures with the immediate forecast, 1-day future forecast, and 2-day future forecast. And the key observation here is that the importance of the features, they change depending on the forecast horizon. So for example, the wind speed is the most critical feature for immediate forecast, while for long-term forecast, the turbine ID is the most important one. So the ID here, it can be seen as a proxy for the turbine location and the turbine-specific characteristics. We can also observe that not all features are needed, and we thus remove both the directional features, so in direction and nacelle direction, as well as the inside and outside temperature features. Moreover, we merged the 3 pitch angles into a single value by taking the maximum value at each time step, since they are perfectly correlated with each other, as can be seen in this heat map here. And the final feature set that we actually use is therefore the turbine ID, the wind speed, the maximum pitch angle, and the reactive and active power. So this is a high-level overview of our solution. It's based on the fusion of 2 very different models. So the first one is a modified version of D-linear, which we denote as MD-linear. And D-linear, it was proposed in a recent paper, Are Transformers Effective for Time Series Forecasting, in May this year. So it's quite recent, and it showed that a very simple network can outperform more complex transformer-based models for long-range forecasting. We call the second model Extreme Temporal Gated Network, XTGN, and it's based on stacking multiple gated extensions of temporal convolutional networks to create forecasts for each wind turbine. And as a post-processing step here, we also perform information diffusion over the nearest neighborhood graph to merge information from nearby wind turbines. And both these models, they use a masked loss function that ignores any missing, unknown, or abnormal values in the input data. So let's take a closer look at the details of each model. We start by taking a look at the modified D-linear. Here we actually perform some additional feature engineering before applying the model. And we specifically split the turb ID feature into 2 separate ones, the cluster and ID features. The clusters themselves can be seen in this figure here. And as you can see, it simply considers the X coordinates of the wind turbines. And we actually tried some more intricate methods, but we did not see any improvements in the final score. The ID feature, on the other hand, it simply considers the Y coordinates within each cluster. And from this, we additionally create a new feature, cluster average, which is the average active power of all the wind turbines within a cluster. This takes advantage of the spatial information to improve the performance and robustness of the model. And for the model itself, it's actually exceedingly simple. We first take the time series of each feature independently and split them into a trend and residual part. And this is done by using a moving average. Then we apply linear layers separately to the trend and the residual, and then sum these together. Finally, we merge the result from all features using an additional linear layer to obtain the final forecast for the active power. And in the final model, we consider the most recent 288 timestamps as the input to the model. Then, to obtain even better results, we actually train 4 separate MD linear models with different forecast horizons. So we have forecast horizons 72, 144, 216, 288. And these are trained and then the forecasts are fused together. And the fusion is done by taking the latest 72 predicted time stamps from each model. So for the first model, we take all the predicted timestamps. For the second model, we take the last 72 and so on to get the final predicted output. So for our second model, it's the XTGN model. It's based on a temporal convolutional network, TCN, where the different layers have different dilation factors, which allows for a large resective field. And the figure here is illustrate the structure on how the input is propagated through the network in a standard TCN. However, to allow the information to better flow through multiple layers, we apply a gated extension of TCN, which is shown here. And it actually uses 2 separate dilation layers with respectively a tan and a sigmoid activation function. This is to control the information flow to the next layer. This is then added to the input and then sent on to the next gated TCN with a higher dilation factor. And we use skip connections to obtain the output of each layer in the stack and add these together. And then after passing it through a convolutional and a linear layer, this becomes our output. And then during the inference phase, we actually have one additional step where we adopt an information diffusion scheme to mitigate the negative effects that a typical data can have on the forecasts. And specifically, we adjust the forecast for each wind turbine by incorporating neighborhood information. So this is the forecast values of the neighboring wind turbines. And this relies upon the observation that nearby wind turbines, they exhibit similar wind power patterns. And in the final version of our model, we consider the nearest 49 nearest neighbors. And then for a wind turbine X with a forecast Y, the final forecast then becomes alpha times Y plus 1 minus alpha times the average wind power of the neighbors. So this is the main idea for our XTGN model. And similar to the MD linear model, we consider the most recent 288 time points as the input. So for the fusion of the 2 models, what we actually found performed the best was just using the average of the 2 for each timestamp in the forecast. We also tried using some other fusion strategies, as can be seen in this table here, where one of the models is used for the first 72 or 188 time points, and then the other model is used on the remaining segment. We also tried including other models such as a light GBM model, which demonstrated good results during the offline testing, but it actually resulted in a worst final score when we submitted it online. And for the figure here, it shows a typical 288 length prediction for a single wind turbine. And as you can see, the forecast of the 2 models in green and purple here, they're actually quite similar to each other. But the fused model in orange is the one that proved to be most robust in the end. Finally, this table here shows some scores on offline testing data with some initial baselines and the 2 baselines provided by the organizers. Here we also have included the light GBM model I mentioned before, And as you can see here, it actually have a better score on the offline data compared to the fused model. We also include a version of the MD linear model where we do not use the four models strategy that's you train on different forecast horizons, but simply use a single model. And as you can see here, the score is actually quite much worse than the MD linear model that we used in our fusion. So to summarize everything, our approach is based on a fusion of two considerably different approaches. The first one is MD linear, which applies time series decomposition and transform the features using an exceedingly simple linear network. Here we also adapt and merge forecast strategy where four different models are trained with different forecast horizons and then merged together. The other model is the XTGN, which stacks multiple layers of gated TCNs and then uses skip connections to merge the outputs from each layer together to obtain the final output. And here we also added an information diffusion to incorporate forecasts from neighboring wind turbines and in this way acquire more robust results. The final forecast is a fusion of these two models, and it's simply the average of the two, which proved to be the best results on the online evaluation. So that's all from me. Thank you very much for your attention.